Hi everyone, this is Vanessa Greer from Wilson Tool. I want to welcome you to Finding the Right Fit, Perfecting Your Nesting Process, which is part of our free webinar series. In this series, we'll be bringing you expert solutions to common sheet metal manufacturing challenges in a convenient online format. You can watch for more topics like this one on issues facing the punching, bending, and stamping industries in the coming months. At Wilson Tool, it's our goal to deliver exceptional customer service along with the most reliable and innovative products and solutions so our customers can be more successful. For a full listing of our products and services, please visit our website at wilsontool.com. In addition to myself, I'd like to introduce Elizabeth Graham, who will be co-hosting with me today. We will be managing and sorting through your questions as they come in throughout the webinar. So don't hesitate to ask questions at any point using the Q&A boxes we have pointed out earlier. We will take the last 15 minutes of the webinar for Q&A, and we'll do our best to get to as many questions as we can. We also have Glenn Sheldis here with us as well to help answer questions during the Q&A. He's another one of our application specialists. Now, today's presenter is Scott Tashney, who is an application specialist for punch tooling here at Wilson Tool. Scott has 26 years of experience in the precision metal fabrication industry. Currently, Scott works with fabricators, machine manufacturers, and distributors around the world to resolve their fabrication problems, using creative tooling solutions and pushing machine capabilities to the fullest. I know he's excited to talk with you today, so at this point, I'm going to hand it over to Scott, who will start our presentation.
Thank you very much. It's a short presentation, so we're going to have to get into it because there's a lot of content we want to cover. Again, finding the right fit, perfecting your nesting processes. Again, and I also want to acknowledge Glenn Sheldis' work putting all this material together. Right now, we're not going to talk about nesting as you see it on the screen right now, the very complicated stuff, but rather, the same piece individually nested, so it's relatively simple. Okay, so to break it down, we're going to talk about parts falling out, generally due to weak joints, sheet shake, and our solutions are going to be tabbing. We have a variety of options there, and then also when and where to use those tabs. Another nesting issue is pinch points, and those are going to be resolved with some tooling solutions. And then part of nesting is nibbling, so you get that uneven wear or reduced tool life that often results in galling as well. Shapes, i.e. piercing tools, then we're going to introduce some lancing or forming tools as part of the solution. A wire tab, as you see, it's very popular, or historically was very popular. It's unstable and does not break cleanly. The tab width is roughly 33% of the material thickness. One would say it's dangerous and should be used as a last resort. Corner tabbing, most common shaker tab, normally created with a rectangle or square punch. Roughly 10% of the material thickness is left in both directions. On the left side, you see it's inserted, the part still inserted in the sheet, and the right photograph throughout these is how it broke away. And that's how we determine that 10% or how it's defined. Another 2D shape would be an equilateral triangle. It's a standard shaped tool, relatively inexpensive. So we're using a triangular tab that breaks cleanly. The tab width is again roughly 33% of the material thickness. And you can see as it's broken away, there's that little pip that we've created. Inverted diamond tool. This is a common special shape tool. It creates a diamond-shaped tab that breaks cleanly. The tab width is roughly 33% of the material thickness again. Again, as you can see, it breaks out, it's going to leave that little pip. a variation of that inverted diamond tool with horns. It's a special shape similar to that inverted diamond. It creates a diamond-shaped tab, breaks slightly below the edge. The tab width is, again, 33% of the material. And the big difference, what you'll see is I'm going to highlight a couple things, is an inverted diamond doesn't have to be the normal, just a sharp point. As you can see, this one's got a nice curved arc. But the big difference is we got this little horn, so it's digging deeper into the sheet. So when it breaks away, when you look at that sheet, nothing really sticks outside from the edge. This is where we get into forming tools. So rather than just a 2D shape, we're going to put a little form up, form down coin on the edge of a tab, normally used for, on a, say, a chamfer corner. So what I'm trying to do is literally just put a little V groove, can be top, can be bottom, can be both, and that's going to create a weak point where we're going to break it away. There we go. I have a hard time advancing here. Another variation of a forming tool goes by a lot of names. Here we're calling it a half shear tool. It might just be a single-sided lance. I'll show you a couple different ways of doing this. But the forming tool, okay. So you can turn that on. Okay, rumor has it we had some audio issues, so I'm moving my location. Sorry about that issue. Actually, I'm going to make sure I clear that by hanging up. Okay, that's gone. Okay. So on these lance and forms and in the coining tools, the big thing that we're really chasing is creating a much longer area of connectivity on our part. That gives us a lot of stability. Now, with these lance and forms or chisel points, it changes the visual a little bit. So you can see I kind of have two little points of where it broke away, as opposed to just one. But it's a smaller indentation, if you will, so it's generally a cleaner look. On that single-sided lance, so here's a profile where you can actually see how the material is moved from being at the sheet level. It's lanced down or lanced up depending on your direction. You can also see how the opening, how that changed. You got those little pips there. This is a sample that Wilson Tool makes and shows with customers, so you can see the difference with this new lance and form design, because it's becoming more and more popular. As you can see, the tab is kind of then gang bent in a press brake. Give you a little bit more close up. So in this case, if you imagine, this tool would have been a true four-sided cutting half shear that was run, and then afterwards brought the cutting tool, brought it up, trimmed it up into that shape. So it's very stable, very useful, and it allows you to do more and more with your fabrication methods. The big strength of getting into these new forming tools or dash tools for forming is it helps deal with this thing we call sheet shake. And here I'm showing you a sheet that's got all the little tabs, corner tabs, and some tabs in the middle. And anyone who runs a punch press will recognize that as I'm moving back and forth in my nibbling operation, those parts can start shaking out of the sheet. So from a programming method, if you didn't have those lance and forms, you can still use your current tools, your current processes. If you tweak that program and not have, we're going to not make that part as small immediately during the process. So I'm going to advance My slide, something popped. Okay, so in this slide you can see how we have more web. We left web in a certain area, so as the machine is running, shifting back and forth, it's much more stable. And after we get most of the sheet punched out, we're going to come back and then remove more material. So at this point, we're going to play a video of this type of operation in process, and you'll see how stable the sheet is while we're punching it. Hopefully it went full screen. I tried to make it full screen, or you might want to make it full screen on your own computer. You'll see a much larger web as it's moving left and right. Nothing falling apart. This part was utilizing corner tabs and then those other tabs that are currently wide, and we're going to narrow them up with this in and out nibbling mode. Okay. Just going to clear my notes here. Okay, another method of avoiding sheet shake is to nest the parts a bit differently. So if this is our part, and we were going to put it in the nest, you know, here's your inevitable or your more common practice. Inevitably, it's going to start shaking apart. What we do is we create mini nests, if you will. So you have those nice, thick webs adding stability to the sheet. So we got 9 little islands there, much more stable to go with. So our summary of tabs that we've covered would be the wire tabs. Some would say dangerous and should be outlawed. Many people have cut themselves on them. Corner tabs, for those, your part has to have a sharp corner to use those. Good sheet stability depending on the tab location. The diamond tabs, they may break at the wrong side, poor sheet stability. The triangle tabs, that requires a auto index station. I probably should have noted that earlier. Better stability than the diamond tabs. The dash tool, different edge look and feel. Some might like it, some might not. Often used on the chamfered corners of a part. The hash shear tab, sheet is formed, which can cause problem issues or programming issues, but good stability and can cure sheet shake as a problem. I said I'd go back to this Wilson sample, and the point of the sample is generally when we're doing this live, we have the hash shear tab where the arrow is, that's where it's being effective, but inside the sheet you'll just see how it would normally hit when it wasn't used in a tabbing situation. And then your triangle, inside you see it's just a triangle tool, and when you use it next to each other you're creating a tab. So that's what we're trying to show you here. And that internal part can break away, and if you broke it away, the outside of that sample, you could run your finger across it and get the effect of these different tabs. So I'd like to take a poll here real quick. I'm curious, which type of tabs do you use today? So this will be our first poll. You have some options. You got about 15, 20 seconds to select some options. You can do many. Give us an idea what you're using today. So hopefully everyone's getting close to making your vote through the polling section of the screen. I'm expecting the poll to close any second. Oh, and then I see there was a second, the second poll also showed up on the screen, so I apologize, I didn't recognize that. So, of the tabs you don't use today, which ones would you like to use? I.e., you know, that hopefully some solutions came through today in today's presentation that you're interested in. Looks like quite a few people still use the wire tab. Corner tab, very popular, I'm seeing. Triangle, diamond with the horn, a couple half shears, some dash. Looks like 2% of people don't do any tabbing. And then, as I expected, what you're not using today, what you might want to go into, like half shears, the dash, and the diamonds have some good feedback. And that's what we're hoping to do today, is show you things that you might not have considered, and you can use them in the future. The next topic related to nesting and slitting, we get those pinch points, those ugly bumps along the side of the edge. Our solutions are twofold. We can do it with 2D shapes, and we can do it with wheel tools. Good ways of avoiding those little pinch points. So they're most commonly caused by slitting or nibbling. Hopefully you can see the pinch points. I mean, it is a common complaint for customers, at least to me it is. Okay, how to resolve it with a standard 2D punch is what we're going to do is, the left image shows you standard process. I'm going to use a rectangle punch and a rectangle die, and that's just a single hit. On the right, you see the image, it's an oblong punch and a rectangle die. So as you can expect, it looks odd because I don't have matching geometry. I get those little push downs. Those are interesting. But the nice thing is when you hit them in sequence, there's our little pinch point when I did 2 rectangles. I'm getting that. You don't see that here with the rectangle die and an oblong punch. Recently I've spoken to some customers who thought they could go with just an oblong and that would cure it. It really requires that different shape. I'm going to go back one slide and show you, it requires kind of really that effect to get rid of the pinch point. So something to consider. Another way of it, avoiding the pinch point is don't nibble, use a shear wheel. We have a variety of shear wheels, different material thicknesses, types, has a wide range of uses, so it's not 100%, you know, it doesn't work in every situation, but it is a very viable solution. There I'm showing you the shear wheel. Another wheel would be a rolling pincher. And I failed to give you a slide on what the rolling pincher does, but what I'll draw it is the wheel has little peaks. It can be top side, it can be bottom side, you know, both. But the point is we're pinching, we're coining that material. So before we go slit, we're going to run that wheel up the side that we want clean. Sometimes you're doing common line cutting, so you need to do both sides. So the image on the top shows you, if I don't run a rolling shear, the one on the bottom shows you when I do run the rolling pincher. I misspoke a second ago. So it's very clear. I've done this for a variety of customers. Some of them accuse me of just zooming in on the photo to hide the pinch point, but samples prove themselves. But you know right here, it's also effective to pre-mask burrs on the bottom side. So it's a 2-for-1, getting rid of pinch points on the top side, and I can hide that burr on the bottom because it never gets to the bottom of the sheet. Here's just a sample that we like to share with customers, give them an idea how we're doing the pinch points using a pincher or a dash tool, and we can even gang them up. So here's 9 parts. Actually, there's 4 subparts in there that we gang together. and they're held together just with, you know, that coined edge, that rolling shear. So a little bit closer setup. You know, we're running those roller pinchers around here, and then as I took the sheet out of the machine, I can snap those apart and they'll break away. So those cures for the pinch points, we got that oblong punch and a rectangle die. But here I'm also noting a long D punch and a rectangle die. And the reason for that is because there's those times when you still need to, you know, create a corner tab. So I'm creating that corner tab. I can use an oblong and an auto index station, bring my two corners together and still have it tabbed together. And then the rolling tools, we got the rolling shear, a rolling pincher. Again, it can be just top side to get rid of the pinch point, but if you do a top and a bottom, you can often hide any burring that may or may not occur. Lastly, in the nesting solution, a lot of times you're segregating parts, you are doing a lot of slitting, uneven tool wear, you can get that reduced tool life, rolled over edges, turns into galling, it gets pretty ugly. The die I'm showing you, you can see the marking, an actual die, and you might pick up on the oddity, it looks like the customer's using it slitting in both directions. That can be a problem. So slitting tools, I mean, there is an intended direction. We're going the lengthwise. If you go the other direction, you're hitting often so little material, the slug twists, kicks the punch to the side. Now you got punch and die contact. You break your tool down very fast. So here's another pull that we want to have. Mainly out of curiosity, do you slit your rectangles in both directions? Yes or no? Oh, did I skip a pull? Apologize. The pull that's up, if you guys wouldn't mind answering it, which methods of dealing with pinch points do you have? I blew by this one. Oblong punch and rectangle die, long D. And then the second question is, of the methods you don't use today, which methods for dealing with them would you like to use? So if you guys wouldn't mind answering the poll from a few slides ago, I'd appreciate it. See if we get some results coming up. Okay, here's our results. Again, there's a fair amount of people who aren't using this method. A surprising number are using the oblong punch and a rectangle die. Some using a long D. Rolling pinchers. And then for those who don't, what you'd like to use in the future, that oblong punch and rectangle die really grew up near 60%. So we'll just move on. Sorry about the delay on that poll. So I want to show you here's the intended direction of the slitting tool, and then kind of that recommended overlap. So we'd like to see a minimum amount of corner rad, because often these rectangles have radiuses in the corner, make them stronger. So it's really corner rad with about a half material thickness. Now the maximum, we don't want to, i.e. take so little material, it becomes problematic, again, side loading. So we'd like to be about that quarter of the tool length, no more than half. I know a lot of people do a lot worse conditions. And I'd just like to make a point. You can save yourselves a lot of tool if you pay attention to how you're stepping over on your slitting. The non-intended progression direction, again, I'm showing it because, you know, I recognize people are doing it. We suggest you don't, you still do it. You really should use a large minimum step over, which is pretty much your width of your punch minus that corner rad, you know, minus half material thickness. We really don't want you to do it, but you're doing it, trying to give you a little better suggestions on how. Because small step values that you can put in your software, there's a max and a min, those small step values are really designed for a round tool, doing a contour to minimize that scallop depth. And that's what I'm showing here. You know, it's that step over, that minimum value, it minimizes that scallop. It's really not appropriate to use that philosophy or, you know, on a shape tool, really just rounds. Okay. Another way of dressing side loading is via the programming. So we're taking away our slits from, you know, that larger nest. We took a 3 by 3 as opposed to the 12 by 12 or 16 by 16, whatever I had there. So we're going to remove the slits, look at that sheet, and how can we change our programming methodology to enhance our tool life. On the top side, you got the traditional slitting, which does produce an unbalanced load. As shown, the rectangle in the right direction, you know, that's the best we could ask for, but it's still cutting 3 sides. You're going to zip right through it. Now on the bottom, we're showing an odd even slitting. So it's going to produce a balanced load by leaving those big tabs. So for the most part, I've taken full chunks, and then I've come back and I knock those out in a backwards pass, cleaning it up, and I have an equal load side to side. Again, that traditional method is going to give you pinch points. So on the bottom, I did the old ob round, rectangle die. You're going to eliminate some pinch points. So then the question is, you know, does your programming software look out for your tooling? You know, everyone's trying to produce a part as fast as possible, but often they're doing it at the expense of their tooling. Now, it's my belief that some offline softwares are recognizing this every other and step back, giving you a little bit better tool life. So the question is, if you want to, you know, chase that, is your vendor going to support you in that decision? If not, why not? So a summary on the slitting is, you know, take the step in the right direction, you know, improving your tool life. Don't go on that narrow step. And then, you know, don't follow the crowd, maybe take an odd approach. You should see better tool life. So in conclusion, we covered the parts falling out by a variety of tabs, selecting the right tab. New designs are out, use them. Pinch points, we had a couple different tool solutions. And then that uneven wear or reduced tool life. So adjusting your programming rules, and don't be afraid to ask your vendors to do something differently that you think is going to save tool life. We're all here to help you. So at this time, we'd like to open it up. We're going to do the Q&A section. So I hand it off to Elizabeth.
Thank you, Scott. And if anyone has any questions on Scott's presentation that they'd like to ask, please go ahead and enter those now in the Q&A box. Go ahead and send those in, and we can respond to those. We'll get to as many of those as possible. The question that we wanted to ask Scott right now is, on the pincher sample, what was the thickness?
The pincher sample that was shown, I believe, was 18 gauge, but it can go much thicker. It becomes how soft the material is, and then what quality of breakaway you want. So realistically, trial and error is the best way to determine how thick it can go.
Can you flip back to that? Slide back to that sample.
Hop back to that sample. There it is. A little too fast.
See, that's also, we've got two entrants. This one and also the slitting one. Everybody can hear you.
Next question.
Okay, well, that's all we have for Q&A. If you guys have any more questions, please feel free to contact Scott directly at scott.tashney@wilsontool.com, or for general questions, you can contact marketing@wilsontool.com.
All right, thank you, Scott, and thank you all for joining us today. We will be sending you an email in the next day or two with a PDF of today's presentation, as well as a link to the recording of this webinar. And you can share that with anyone who maybe didn't have a chance to come on today and listen live. You'll also be able to find the recording of the webinar in our Media Center on our website. We look forward to hosting you at future webinars in this series, where we will provide expert solutions to common sheet metal manufacturing challenges. Have a great day, everyone. Thanks again.